Hello, welcome to Apple Plus, the Android on Chromebooks. I'm Garfield Tan, a software engineer on this project. First, let's have a brief look at the reason why we decided to do it. So Chrome OS has been focusing on web content for a long time, and we acknowledge that we also needed apps because offline use is still necessary, and web content can't fulfill all needs users had. In order to bridge that gap, we turned our eyes to Android, a mature ecosystem on which Google had a big impact. In 2014, we released App Runtime for Chrome, or ARC for short, based on native client that emulates the runtime environment of an Android app. It wasn't very successful due to the tech limits. Additionally, Android was also evolving, so it was impossible for Chromium OS devs to closely follow their steps. So we changed our technical direction and introduced Apple Plus as the conceptual successor to Apple Plus, hence, the Apple Plus. We are running a copy of Android system on Chromebooks instead of leveraging browser technologies to emulate the runtime. Nowadays, when we say ARC, it usually refers to Apple Plus, actually. The old ARC is usually called the legacy ARC or the ARC welder. So Apple Plus is the main topic of this talk. And let's move to it. This is the agenda. I'm going to cover those 4 topics in sequence. First, let's dive into Linux containers. We briefly discussed the low-level sandboxing mechanism we use for Apple Plus Pi. That's a Linux container-based solution. The famous Docker is using the same technology as well. When it comes to Linux kernel, it actually offers a bunch of namespaces listed in the slide. It's used to isolate access to certain resources from a group of processes. Apple Plus uses all of these namespaces to isolate Android from the rest of the system. Therefore, Android and Chrome are sharing the same kernel, but Android cannot see that Chrome lives beside of it. Ideally, Android doesn't know it's running in a container, but since we are using the same kernel for them, there are certain type of syscalls we don't allow. For example, there's a quota CTL2 that install-d uses to get per user disk usage. And install-d is the daemon in Android system that installs the applications to it. This is what one sees on Chromebook in a developer mode when running PS3 in a terminal session. Init process is the first process Android system runs. Its descendant processes are isolated inside a container and can't see the rest of the system, but they are visible from out of it because they need to communicate with Android processes. We won't dive too deep into details of the low-level sandboxing technology because I'd like to reserve some time for the most different thing between Android and Chromium OS, that is window management. So the next topic will be about window management, but before we dive into it, we need some basic knowledge of Android window management as a preparation for the introduction to the work we did to bring Android apps to Chromebooks. The first one is activity. It's the first concept one learns when they learn Android development. Coarsely speaking, using web terms, it's basically a page that an app shows to the user. For example, when a person buys something, they put something in cart and go to checkout page to put the order. In Android, it'll be the user putting the product into cart in product detail activity, checking items in cart activity, and putting the order in checkout activity. Any activity has a life cycle as shown on the figure that is managed by Android frameworks. This life cycle is usually alien to web and PC app developers, but it's actually a powerful tool to manage resources in environments where resources are limited, such as phones. Android anyway was designed for phones that were from 10 years ago, and the resources were pretty limited there. Activities that are occluded by other activities don't need to keep any graphical resources when it's stopped. but still keep the data to restore them when they are in the foreground again. The second one is window. As the name suggests, it's the most fundamental unit where Android window management manages. Anything inside a window belongs to the view hierarchy and is managed purely by the application. Almost every activity has a window, but there are windows such as some dialogues and pop-up menus that don't have a backing activity. Each window draws its own content and swaps the graphic buffer with a compositor called Surface Flinger on Android. To avoid confusion, I'll refer to this window as Android window and call the window in Chromium Chrome window. The last one is task. There isn't a corresponding concept in web or PC apps, so we have to spend some time to describe it. It represents a job user is performing, and it's a stack of activities user opens to perform it. Let's take the online purchase example as well. Buying a specific item is the job the user performs. So in Android, there's a corresponding task for it. The task starts from projected detail activity, and on top of it, cart activity, and lastly, checkout activity. If in the meanwhile, the user is writing an email in Gmail and picking a file for attachment, the task looks like the figure on the right-hand side. The bottom one is the Gmail activity for writing an email, and then on top of it, it's a file picker. On phones, most of the time, there is only one foreground activity. The task the activity belongs is the only foreground task. Android frameworks swap tasks per user instructions between foreground and background and keeps the order of activities in each task intact. Now we have enough knowledge about Android to discuss the work Apple Plus did to bring Android apps to Chromebooks. We use WLAN protocol as the display protocol between client and server. As one may know, Chromium OS has a component called Exosphere. That's a WLAN server implementation in Chromium, backed by Ash, the Chromium window manager. Android on Chromebooks and the Linux virtual machine Crostini are all its clients. It's a rather unique piece of work to make Android, a system designed for phone at first, a WLAN client, and I'm going to talk a bit about it. The very first question we need to answer is what constitutes a window in Chrome? While dialogues can be put in a separate Chrome window, it'd be very weird to put a pop-up menu in such. So Android window isn't actually equal to Chrome window. On the other hand, Android task is. It is natural for the user to only use one Chrome window to perform one job. And since Android doesn't change the order of activities in a task, it's safe for the user to drag tasks and change their focus without fear of Android frameworks messing it up. Then the next question comes, how do we draw a Chrome window from our Android task? Remember that an Android task consists of multiple activities, which means it also has multiple Android windows. A typical task looks like this figure. The topmost activity is in resumed state, and it has some transparent or translucent part. The activity below it is in paused state and still needs to draw its content to fill the transparent and translucent area. Any activity behind the second one is in stopped state, as there isn't any need for it to hold on to any graphic resources. Finally, there is a dim layer that prevents the task from being fully transparent. On the other hand, Exosphere, the WLAN server, expects to swap graphic buffer with each window. That means we need to composite those Android windows into the same graphic buffer and swap that with Exosphere. The composition is done in Android compositor Surface Flinger, but instead of compositing everything to show on display, we need to only composite each task into a Chrome window. So we had some modifications in Surface Flinger to fulfill the need. This is what a task looks like if there's a dialog window on the top. This is just to illustrate what it is like when there's an Android window without backing activity. Nothing so special about it. System dialogs don't belong to any task. They don't belong to any activity either. So they become independent Chrome windows and they are on top of everything else except the app launcher. In order to explain the architecture of Android on Chromebooks, we need to take a look at the Android system architecture. As I said before, Surface Flinger is the compositor. Input Flinger is in charge of dispatching input events to Android windows. They are the common components for all Android devices. Things in system processes are the common parts for all Android devices. Things in HAL are device specific. Gralog is the graphic buffer allocator. HW Composer, or the hardware composer, is HAL component that leverage hardware capability to perform composition tasks, such as scan-out and hardware overlay. In order to pipe those information to Chrome, we change the structure of it a little bit. So we introduced a new component in HAL layer. We call it Wayland service, but it's actually the Wayland client for Android. It's a hub of window management information for Apple Plus. It translates Windows state requests to requests into Android frameworks, helps dispatch input events, and act as the hardware composer that composites Android tasks into Chrome windows. In those graphs, everything below them are actually dependencies of the things on the top of it. That is to say, Exosphere is actually based on Ash, and Ash uses Ozone. Ozone, in this case, uses FDev. But in previous slide, the input dispatcher in Android gets the event from FDev directly. But we changed it so that it's actually passed through the Wayland service. So is the compositor. We actually swap the graphic buffer with Exosphere in Chrome instead of it talking to the kernel directly. So this is a flow of a Windows state change in Apple Plus, such as maximize. So first, user clicks on the maximize button on the window, and Chrome receives it. And Chrome's posts the maximize request to Wayland service. Wayland service translates it into Android framework requests and posts it to Android frameworks, which is like Android Window Manager service in particular. And then it actually configures the application so that the application can draw its content in a larger window. It also tells Surface Flinger to reposition the application and resize it so that it covers the entire display. And then the app finishes configuring itself and redraws, posts the frame to Surface Flinger. And the Surface Flinger, in turn, posts the frame to Wayland service. And the Wayland service, in turn, posts the frame to Chrome. When the Chrome detects the surface size changes, it commits the maximized states and finishes the entire flow. Then I'd like to share something we saw after the project launched. First of all, the project did its job. It introduced tremendous amount of apps to Chromebooks. I so wish the story ended here. But you know, those apps were developed for phones in the first place. And phones and PC just bear so many different traits. So a lot of apps just don't work for PC out of the box. Would you ever consider keyboard, mouse, and touchpad support when developing apps for phones? Would you consider how it looks when it's maximized on 30-inch monitors and in landscape? it turns out not everyone did, at least. We'll talk about 3 important aspects we would like Android developers do better if you want one to better support Chromebooks. First of all, it's input compatibility. Many apps just don't handle mouse and keyboard events. Chrome OS has a fallback mechanism so that when certain keys are handled by applications, system can respond to it. For example, there's a Control+W shortcut to close the window. Some apps do handle the key events, but they eat keys they don't handle, which just invalidates the fallback mechanism. And appears to be the user as a Chrome not responding to keystrokes. Chrome OS also has a special refresh key that most keyboards don't have, and we convert that into keycode_refresh on Android. So we recommend binding that keystroke and content refreshing. Touchpad is even worse because we have gestures on them. Chrome OS recognizes some touchpad gestures on ozone layer, but Android just leaves everything to applications. Android's general approach is to offer support in the same way to touchscreen as much as possible, but it has some caveats. First, there isn't any single finger gesture on touchpad because it's used to move mouse cursor. So a 2-finger gesture is used to scroll stuff, while 1 finger is enough on touchscreen. Second, touchpad gestures should always be handled by the view under the mouse cursor, but touchscreen gestures can be handled by multiple views depending on the initial location of each finger. ARPA Plus tries to be as compatible with Android as possible to synthesize gestures for scrolling and pinching to zoom. If it makes sense, it'd be great if Android apps can support it and also leverage the multi-finger touch gestures on touchpads. One can detect the source to distinguish events between touchscreen and touchpads. Touchpads events are from source_mouse, and touchscreen events are from source_touchscreen. Then we have layout issues in freeform or large screens. These are just some examples of issues we've run into before. They might already be fixed, but you can get a sense of what type of issues they are. The biggest reason behind it is the misuse of API. API misuse isn't rare, not only because developers don't bear PC environments in mind, but also some interesting history behind Android API. We have display get size and display get real size. I don't think anybody can get a sense of what they really do behind the scene. It turns out display get size actually returns the window size if it's a freeform window. The reason behind that was Android window was almost taking the entire space on the phone. So it could be a display size, like it could be interpreted as a display size, but it actually minus the status bar, which is on the top, and the navigation bar, which is on the bottom. And when it's transformed into freeform windows, we need to cut more things so it becomes a window size instead of a display size. But how would somebody know that just from its name? And on the other hand, display get real size returns the actual display size that also includes the system decorations like a status bar and navigation bar on Windows phones, on Android phones, and the app launcher on ARPA Plus as well. According to Stack Overflow, there are more than 35 ways to get a display size, and 32 of them were uploaded, but only one of them is correct. I'm glad that get size was finally replaced by Window Manager get display metric, get current metrics in Android 11. That is not an isolated case. I mean, we also have view get locations in surface, view get location in window, and view get location on screen, and such and such. They are pretty confusing as well, and all of them are well documented. Android has been deprecating obsolete ones and improving documentation on applicable ones, and we already see some progression there. So pay attention to the update to the Android documentation and use the right one. Another thing that is related to API misuse is the app should be display aware. Density difference between displays, there's a primary display and external display, can affect the window layout a lot. Be careful with that. Next, be aware that the app may be resized after launched. Handling configuration changes in code offers the most responsive result to window resizing. Using different layout depending on the screen size to better leverage large display real estate is a minimal requirement. Make sure you handle activity recreation if you choose to do that. Be aware, this is not only for Chromebooks, but also important for good support for the new, shiny, foldable Android phones. It'll be pretty hard for the user for you to avoid window size changes after foldables and are launched on Android. Last but not least, there are apps on games who have native libraries only available in ARM. That's okay because there's a translation layer that translates ARM instructions into x86 instructions. But it's not as performance as native libraries. So to provide the best performance, considering offering all 4 variants, which is ARM and x86 times 32-bit and 64-bit. Play Store only serves necessary libraries to devices, so don't worry about downloading sites. In addition to all of above, we have more content for you to refer to if you want to learn more about how to do Android development on Chromebooks. And with that, I'm going to go over to Q&A. Thank you for your attention. And if you want to post questions, there's a link on above that you can click. So the first question is there a restore functionality between Android apps on CB and phones? For example, if I'm playing a game on my phone, can I continue on my CB? For the time being, there isn't. But that's definitely something we can look at. The second one is, how can I request a feature on Apple Plus if I'd like to know the refresh rate of each Android app running on Chrome OS? Can Apple Plus expose relevant info to Chrome OS? So it actually is related to the graphic buffer. So I need to go back a little bit to the slides. So here, it's actually the Chrome that drives the graphic buffer swaps. So Android is kind of passive behind the scene, and so Chrome OS already knows the refresh rate of the Android application. And there's actually performance tuning tool. And if you want to refer to, it's actually covered in our past IO 19. You can use that to fine tune your games. It actually has the information that you need to like that includes refresh rate, and it also has like frame posting and those type of stuff. That's in Chrome OS. I think that should be it. Thank you.